Good afternoon and welcome to Live from NOIRLab at Kitt Peak. I'm your host, Rob Sparks, with our moderator, Jamaica Marshall. Our guest today is Aaron Meisner of NOIRLab in Tucson. He's going to talk about a neat citizen science program called Backyard Worlds and how it helps astronomers discover other celestial bodies. Remember, if you have any questions or comments, you can enter them in the chat box and we will relay them to Aaron for you. First, I'd like to tell you a little bit about Kitt Peak, since this is live from NOIRLab at Kitt Peak. For those of you who might not know about it, we are funded by the National Science Foundation and the NOIRLab facility. It was founded in 1958 and is located about 55 miles southwest of Tucson on land leased from the Tohono O'odham Nation. We are indebted to them for letting us use one of their sacred mountains for astronomical research. Kitt Peak is home to 24 optical telescopes and 2 radio telescopes. I'd like to also start off by just sharing a brief science highlight from the last week or so here. And this is a surprisingly dense exoplanet that we found. New observations of exoplanet. The Hubble Telescope, McDonald Observatory, and other facilities. They raise new questions about current theories of planet formation. The exoplanet has been found to be unusually dense for its size and age, raising questions about how it came to exist. This planet is slightly smaller than Neptune. K225b orbits an M-dwarf star, a small cool star, the most common types of stars in the galaxy, in 3.5 days. The system is about 600 million years old and located about 150 light years away from Earth, relatively close on a cosmic scale. Astronomers predict that giant planets formed by a modest rock ice core about 5 to 10 times the mass of the Earth, and then enrobing themselves in a massive gaseous envelope hundreds of times the mass of the Earth. The result of this process is a gas giant like Jupiter. But K225b breaks the rules of this conventional picture, with mass 25 times that of the Earth and modest size. K225b is nearly all core and very little gaseous envelope. These strange properties pose 2 puzzles for astronomers. First, how did K225b assemble such a large core? Many times the 5 to 10 Earth mass is the limit predicted by theory. And second, with its high core mass and strong gravitational pull, how did it avoid accumulating a significant gaseous envelope? You can read the full press release on our website at nationalastro.org, which also goes into how they used a very inexpensive device called a diffuser to help with these observations. It's a really neat story, but it's a little bit more involved than we have time to go into at this point. So I'd encourage you to go to nationalastro.org to see what that diffuser helped out. So now I'd like to meet our special guest. Dr. Aaron Meisner is an astronomer who works at NSF's NOIRLab in Tucson, affiliated with Kitt Peak National Observatory. Physics from Stanford University, has earned his PhD in physics from Harvard University. Before joining NOIRLab's scientific staff, he was a NASA Hubble Fellow at the National Optical Astronomy Observatory, a predecessor to NOIRLab, if you will. And I will stop screen sharing at this point and bring Aaron on and let him take over. So let me find Zoom so I can actually get my screen share undone here and let Aaron take over. Oh, come on, why can't I? Did I stop sharing screen successfully? Yes, I did. Aaron, are you there?
Yep. Starting screen share momentarily here.
Aaron, you can share your screen and start your presentation.
Are you seeing this, Rob?
Yes, you're good to go, Aaron.
All right. Well, thanks, Rob, for the great introduction and the background material and the very interesting news coming out of Kitt Peak in the past couple of weeks. So today I wanted to talk about the work that I've been doing specifically on a citizen science project called Backyard Worlds that I helped co-found a couple of years ago. And Backyard Worlds is all about taking huge survey data sets from both space and from the ground, for example, from telescopes like the Blanco and Mayall that are associated with NSF's NOIRLab, and looking for cold nearby worlds in the general vicinity of the sun, either hypothesized planets in the outer reaches of our own solar system, like the artist rendering shown here, or what are called brown dwarfs, which are kind of like in between planets and stars that can be very cold and very faint and lurking unseen until now, very nearby our own solar system. So one possible stereotype about astronomy is that astronomers really like to search for new planets in our solar system. And to some extent that really is true. This is kind of a timeless quest throughout many centuries of astronomy, is to predict and then actually find with telescope observations new planets far out in the outer parts of our own solar system. And one thing that may be a little bit surprising about this, at least, is that Neptune, discovered in 1846, is actually the only ever case of a planet in our solar system that was found based on a correct mathematical prediction. So you may
Aaron?
have,
yeah. I'm not seeing your presentation. It's a black screen right now.
Oh, okay.
There we go. Yep, now I can see it.
I'll just leave it like this then. Right, so just to review, a sort of timeless quest throughout all of astronomy has been finding new planets in our own system. And so Neptune is actually the only case, as shown here, that was discovered in 1846, the only case found by a correct mathematical prediction. Whereas Pluto was a chance discovery in 1930, and it was based on faulty predictions of a new distant planet in the outer solar system. So the prediction wasn't correct, but nevertheless, it led to the discovery of Pluto, although we now do consider Pluto to be a dwarf planet rather than properly the 9th planet in our own solar system. Despite these past hardships and failures, there are still some additional new theories of planets that may be lurking unseen in the outer parts of our own solar system and have not yet been detected. And so I wanted to highlight a couple of them here. One is called Planet 9. This is a hypothesis advanced only recently in 2016, and a few years earlier, also based on some Blanco data actually from a NOIRLab facility. And so you can think of Planet 9 as being kind of like Neptune, but 20 times further away. So many hundreds of astronomical units away from the sun, where one astronomical unit is the distance between the Earth and the sun. So this picture shown here is two Caltech professors who helped advance this theory, Mike Brown and Konstantin Batygin. And one interesting thing about Mike Brown is that he's largely credited with the demotion of Pluto from its previous status as a planet to its current status as a dwarf planet. So on social media, for example, his handle is Pluto Killer, which is kind of an amusing way of trolling, I guess, the skeptics who still say that Pluto is a planet. And then the other version of this is what I refer to as Planet X. And you can think of this as being like Jupiter or maybe even Saturn, but 5,000 times further away from the sun than Jupiter. So this is way, way far out in the solar system, potentially even in the Oort cloud. And so one thing to keep in mind about both of these scenarios is that in each case, the hypothesized planet would be in the very cold outer regions of our solar system. So when we think about the temperatures of different celestial bodies, there's sort of a continuum that emerges between, say, stars on one end, like the sun, which is many thousands of degrees in temperature, so very hot. And then you can go to much cooler red dwarf stars or M dwarf stars. An example shown here is WSA 229a. And you can actually go even fainter and even colder than that to a class of objects called brown dwarfs that are intermediate in size. By size, I mean mass, really, between the largest giant planets and the smallest stars. So as you go from larger to smaller, you also go from brighter to fainter. And another thing that happens is that the peak of the light emission also shifts from the visible into the infrared portion of the spectrum. And so when you're thinking about how you might go about detecting something like a very cold brown dwarf or planet nearby the sun, you start to be really interested in having data specifically in the infrared wave bands, because that's where these types of celestial objects emit most of their light and are best detected. So fortunately, over the past decade or so, there's been somewhat of a revolution in our view of the infrared universe. And this is thanks to a NASA satellite called WISE. So I'm going to play a little movie here. So this is a picture of WISE. It's actually a rather small telescope. It's only a 0.4 meter aperture. So, you know, telescopes on Kitt Peak are like 100 times more collecting area than that. But nevertheless, because it's in low Earth orbit, as seen here, and it's in space, it has great sensitivity in the infrared. So it orbits around the Earth once every about 90 minutes. And as it's doing that, it scans in these large circles across the entire sky. And then as the Earth goes around the sun, you sort of map out different, slightly overlapping, but progressing circles on the sky over time in such a way that every 6 months, you create a new full sky map in the wavelength range of about 3 to 5 microns. So for reference, that's kind of like 10 times longer wavelength than what we think of as visible light. So here's a little animation just showing the progressive way in which WISE builds up its coverage during each 6 monthly sky pass to make more and more full sky maps over time. So WISE was launched in late 2009, but it's still observing as we speak. So not only is WISE a really great resource for infrared astronomy, but it's also a great resource for time domain astronomy because it's mapped the entire sky now more than a dozen times. And that makes it really, really great for detecting objects that say vary, so their light curves show changes in flux, or they move, so they're changing position on the sky as a planet would do or as a nearby star or brown dwarf would do. So WISE has already had an amazing legacy of revealing sort of historic discoveries of these cold objects known as brown dwarfs nearby the sun. And this is just a visual illustration of that. Sort of near the bottom center, you can see the sun, but then you see also some relatively famous by astronomy standards stars. So Barnard star, Alpha Centauri, Proxima Centauri. These were all discovered, you know, over a century ago by now. And these are still the closest known neighbors to the sun. So it was almost a century before WISE started revealing more of these brown dwarfs that are similarly close to us, but had been missed because most past searches were in visible light where you just can't see these cold objects. And so in 2014, there's this object WISE 0855 that was discovered. It's the coldest known brown dwarf, about 250 Kelvin. So it's like, you could think of it as being as cold as the North Pole or something like that on Earth. And that's now the fourth closest known system to the sun. Then there's this binary pair known as Lumen 16 or WISE 1049, discovered in 2013. That's now the third closest known system to the sun. So the question that this raises for me is if we really searched to the full depth of the entire trillions of pixels of WISE data that we have now, would it be possible to find more objects like this, or even objects that set a record for being closer than Barnard star and Proxima Centauri? So that, I think, is really what captivates me about this WISE data set in relation to finding these cold brown dwarfs in the solar neighborhood. And what I think also is a lot of fun for the participants in our Backyard Rules project. So I just wanted to show a quick visual highlighting the way that this type of search for either planets or brown dwarfs has been done in the past. I call this the sort of old-fashioned way. And the basic idea is just to look for things that move, because everything in the universe is indeed moving, but the things that are closest to us, just based on perspective, we'll see them move relative to the background of much more distant stars and galaxies that appear to remain fixed. And so this example shown here is Barnard star. Its motion was discovered in 1916, and it remains the fastest known apparent motion of any star or brown dwarf. But you know, it's exciting to think that WISE could potentially change that going forward if we search the full data set. Another example of this on the planetary side, really the dwarf planet side, is Pluto. So this was a famous situation where Clyde Tombaugh really diligently and painstakingly flipped through huge amounts of images to single-handedly make this discovery. And what you see with the arrow pointing to the small dot in this picture is that Pluto is moving quite a lot relative to the background stars. And that's how it was discovered in essence. So it may be surprising to know, but actually the sort of old-fashioned approach of just staring at images is still state-of-the-art among professional astronomers. It's a very time-consuming process. So what I'm showing here in this picture is what we call a finder chart. And this is what's typically been used, say, going back 5 or 10 years ago to do brown dwarf searches in the WISE data set. And teams of professional astronomers, 5 or 10 years ago would take millions of these or many hundreds of thousands of these and have one sole astronomer or maybe a very small team of a handful of people look through all of them manually to see whether anything was moving, which is kind of mind-boggling to me. And it really made me think about, this is a perfect example of how crowdsourcing can really come in to the benefit of scientific discovery, because we now have the internet where we could take these hundreds of thousands of pictures and distribute them among many thousands of volunteers and have it be sort of a lighter load and a more fun experience for everyone. The other thing I would note about this finder chart is just that even I, as a professional astronomer, have a lot of difficulty parsing what's going on here, because you just see this sort of mass of different image cutouts shown at different times and at different wavelengths with all these little circles on them. And even I have a difficulty in sort of interpreting what this is supposed to mean to me. So I think there could be better ways of doing this, and that's part of what we wanted to do with Backyard Worlds. Of course, citizen science or amateur astronomy has a long history in astrophysics. You might think more of this in terms of potentially like backyard observatories in the past, many decades ago, where a small handful of people have the technical capabilities to sort of set up their own telescopes. And so one example of this from Arizona, being that I'm in Tucson, is Thomas Bopp, who famously co-discovered Comet Hale-Bopp in 1995. But nowadays, going back to this crowdsourcing theme, you don't need a telescope in order to contribute to cutting-edge scientific research, cutting-edge astronomy research. And one example of this is what's called the Zooniverse web platform for people-powered research, as they call it. Zooniverse hosts many dozens of astronomy projects where essentially images or movies are distributed to large numbers of volunteers who then help sort the data or make new discoveries in it. So this again leads me to believe that the field of solar neighborhood brown dwarf discovery is really ripe for this sort of crowdsourcing citizen science online approach. So I wanted to highlight a few really fun examples of previously successful Zooniverse crowdsourcing projects. One is Galaxy Zoo, which you may have heard of, and they have had many discoveries, but one of the most famous is what's called Hanny's Voorwerp, which was discovered in 2007 by a Dutch volunteer. And this was a totally new class of astronomical object that no one had really known about. And it was only found thanks to people staring at images very intently and noticing it and then bringing it to the attention of professional researchers who then went and looked at it with Hubble and other big telescopes. Another one you may have heard of is Tabby Star or Boyajian Star. And this was discovered in 2016 by the well-known Zooniverse Planet Hunters project. And it was at a time considered, one of the most well-known stars in our entire galaxy, because there were all these ideas floating around in the media about, was it alien megastructures or all these very bizarre theories that you might have. I think more recently, it's turned out that this is probably explained by just dust enshrouding the star. But nevertheless, it's a kind of iconic example of how having lots of participants scouring the data can give you new groundbreaking discoveries. So that leads me to how we're trying to do the same thing with Backyard Worlds. There's a little movie that plays here. This is our Backyard Worlds interface on the Zooniverse platform. You can access this at backyardworlds.org. This link shown at the bottom. So what you see here is what we call a flip book, and it's basically just showing you an animated movie of what you see on a small patch of the sky. So this patch of the sky is even smaller than the size of the full moon. And of course, we have the full sky worth of these little cutouts. So quite a lot of data to look at. And this specific one is showing that same WISE 0855 object, which is, you can see my mouse at all, there's this orange dot that's moving across the screen. And so the idea of Backyard Worlds is to look at these flipbooks, which are showing WISE data, and to try to find other examples of these super cold Earth temperature brown dwarfs nearby to the sun. So just a little bit of background. This was a project that I co-founded with these others from NASA in Mark's case, American Museum of Natural History in Jackie's case, and Arizona State in Adam's case. And we launched in early 2017. So we've been running for a little over 3 years now. So in addition to our primary Zooniverse interface, the other thing that we've seen come about, which is really great, is that many of our volunteers have lots of interesting skill sets, including technical skill sets. And so one case of this is Dan Castleton, shown here, who's one of our citizen scientists on Backyard Worlds, who comes from Silicon Valley in terms of his day job. And he made this really amazing interface that we now call WiseView, which is kind of an alternative way of looking at the same WISE data that we show in our Zooniverse flipbooks. And you're again seeing here the same example, WISE 0855, but shown in WiseView. It's the orange bright object that's moving very fast from left to right across the screen. So I think this is a really great example of how we had some expectations going in of what this project might look like. But then, we really benefited from the talents that others brought in that we probably couldn't have done ourselves. Certainly I don't have the coding expertise to rig up an amazing interface like this to look at the data. So I just wanted to mention some sort of numbers about how well Backyard Worlds has been doing in terms of sort of engaging with many enthusiasts who are interested in this mission of finding cold nearby objects. So we've now had over 6.5 million classifications on the Zooniverse interface, which is a classification is kind of like one unit of looking at one flip book, essentially. We now have over 60,000 registered users. The number of actual contributors is probably several times larger than that, so well over 100,000. We've had participants from all 50 United States, plus Puerto Rico and Washington, DC, and participants from 167 countries worldwide. And shown at the bottom here is Michaela Allen, who is one of our top participants, who was so good that we actually had her become a NASA intern at NASA Goddard Space Flight Center, working with our science team for a summer. So that's been another fun connection that we try to find various ways to use the talents of all the different participants and bring them into the project in as many ways as possible, whether it's through their coding expertise or becoming actual members of the professional science team. So just to spotlight a few more of our Backyard Worlds participants here. Again, we really have quite a lot of geographic diversity here and people coming from all over the world. We have weekly hangouts where we invite not only the professionals on the science team, but also all of the participants. And so we often generally have actually, participants from all different time zones, all different countries, which is really, really fun. Just to give a little bit more of a sense of the different sort of training or experiences people bring to this, we have participants who are ranging from high school students, college physics students, retired bioscientists, computer technicians, data scientists, lung doctors, you name it. It's really great to have all these different perspectives coming in and taking a different way of looking at our data, which really helps to maximize the science and the discoveries that come out of our project. So moving on from the sort of public engagement aspect to the science aspects, we've had a lot of success so far in discovering and publishing brown dwarfs by mining the WISE data in this Backyard Worlds manner. So this was our first discovery. It was published only a couple months after we launched. I believe Chris Lintott of the Zooniverse told us it was a record for fastest time between publication of a scientific result in a peer-reviewed journal and the launch of the project. And so this object we referred to internally as Bob's dwarf. It has a more formal telephone number of WISE J1101 plus 5400. Was discovered by Bob Sanders, who's a science teacher in Tasmania, as we came to find out. And this is sort of a 1200 Kelvin brown dwarf. So that's 4 or 5 times colder than the sun. It's about 100 light years away from the sun. You can see in this image blink that it's moving around, which is how we spotted it. And what's shown here on the left is a spectrum that we took. So we took the discoveries that were made by our participants and we applied for telescope time at all of the premier telescope facilities, both on Earth and in space. And this includes many from NOIRLab. In this case, it's NASA's IRTF. And so we obtained telescope time there. And our team member, Jackie Faherty, got this really nice spectrum confirming that not only is this a orange looking cold object in the WISE data set, but it has a spectrum that makes sure that it is indeed a brown dwarf nearby to the sun. So I just want to spotlight some of the other examples of this. There's some more videos that I'm just going to try to play real quick. Oh, looks like it won't loop. Anyway, these are some other examples. You can see at least one loop of the videos here that show the type of discoveries that we're looking for in backyard worlds. Looks like the bottom right one appears to want to loop. So anyway, you can see from that one at least that what we're really interested in is that you have this orange bright object that's moving in the middle relative to the background stars and galaxies, which are the general black data points that are just kind of sitting there. And then there's this noisy sort of whitish background that's just nothingness. It's no stars, no galaxies. And so you have to look at quite a lot of satellite data and telescope data in order to find one of these orange things moving around that we're so keen on finding. But when you do, it really strikes you, and it's really gratifying to see after all that searching. See. So here's another way of looking at this. In this case, I sort of switched up the color scheme so that the background is dark rather than light, but it shows the same idea. This is about 20 of our discoveries made by Backyard Worlds volunteers, showing very cold brown dwarfs that are newly discovered. And you see in the middle of each of these panels, a orange dot that's moving slightly relative to the whitish colored background stars and galaxies. And that's, again, exactly what we're looking for. So Backyard Worlds has actually discovered now about 1,700 of these. So you would have to make about 85 pages worth of these to show all of our discoveries, which is quite remarkable and cool, I think. Here's another way of looking at the discoveries made by Backyard Worlds citizen scientists. Again, this is the full sample of 1,700. This is a 3D volume rendering where each Backyard Worlds brown dwarf discovery is color-coded by what we think its temperature is. So red means colder. And then what you see here is that over time, these objects disperse themselves in the galaxy, our Milky Way galaxy. And this is because the brown dwarfs are moving relative to the sun. And so over time, they're going to move away from us into other parts of the galaxy. And other brown dwarfs that are currently far away will start to move close to us. But the timescale shown here for these motions are sort of like millions of years. So this is really a major time lapse. The other cool thing to keep in mind about just how many discoveries we've been able to make with Backyard Worlds is that if you cost it out, we've made sort of 1.3 brown dwarf discoveries per day, which is really awesome. And so Backyard Worlds isn't just about the discovery process. We also need to do a lot of what we call follow-up detailed observations with large telescopes on Earth and in space to confirm and further study the discoveries that are made by our participants. So one example, there are many examples of this, and really we've had time awarded to our project on virtually all of the premier telescopes on Earth and in space. And this includes several from NOIRLab, including the Blanco 4-meter telescope in Chile, which is the panel in the upper left of these images mashed up together. And then in the upper center is the Gemini 8-meter telescope in Hawaii, which we've also used for our follow-up. And then in addition to these NOIRLab facilities, we've also used Hubble, which you may have heard of. That's NASA's optical grade observatory. And we also got observing time for Backyard Worlds discoveries on NASA Spitzer, which is the infrared grade observatory. And also Keck on Mauna Kea in Hawaii, which is considered by many to be the premier ground-based observing facility anywhere in the world, right up there with Gemini. So it's been really awesome to think about the fact that we've been able to point the Hubble Space Telescope and the Spitzer Space Telescope at sky locations that were chosen by our volunteers, which I think is super awesome. So just to summarize the Backyard Worlds component of this that I wanted to highlight, I would say that citizen science is becoming a very important discovery catalyst in this new era of large astronomical data sets and large, what we call surveys, where we're taking telescopes and looking at very wide swaths of the sky. So I think this dovetails very nicely with a lot of the things that are going on at NOIRLab, especially the upcoming Rubin LSST effort, which is going to survey the entire southern sky once every 3 days and get many petabytes of data. I think we'll definitely want to have citizen science projects to help us mine that data set. And similarly, I would say for the upcoming dark energy spectroscopic instrument that I actually work on that's being installed at Kitt Peak. So I would also say that you can help us make more discoveries, and we could always use more help. There's just so much data. As I said, WISE continues to observe to this day. And so we're just constantly getting this flood of data, trillions and trillions of pixels of it. And, it would be really, really great to have more participants come in and join our science team and join in the fun. So I just wanted to have a couple very last slides here to highlight, you may be asking, what is the Kitt Peak connection here? Because I've talked a lot about infrared astronomy, especially from space. But there is a very strong Kitt Peak connection, and it's through what we call our legacy surveys here at NOIRLab. So this is a series of actually 3 surveys done from 2 telescopes that are at Kitt Peak, the Mayo 4 meter and the Bach 2 meter. And then also the twin of the Mayo, which is in Chile, called the Blanco 4 meter. And they have these various acronyms, BAS, DCALs, and MZLS are the survey names. And so these are many tens of thousands of pointings each, so tens of thousands of pictures of the sky each. And in total, this sums up to cover about half the sky. And if you think about it, it's actually been about 1,000 nights in total of observing that went into all of this data gathering effort. And so 40 of those were actually me personally going up to the telescope and doing some of this scanning of the sky myself. And so it's been super fun as part of Backyard Worlds to be using some of the data sets that we made for this legacy surveys effort, one of which is actually these WISE maps that I've been showing you. And so a very cool way that we've explored these data sets with our participants is through the Legacy Survey Sky Viewer shown here, which is been sort of built as like an expansion pack for touring the universe interactively. It's really, really great. I've zoomed out all the way here so that you can see a full sky map of WISE in the infrared, but you can zoom all the way in to the point where you see individual stars and galaxies. And then similarly, this is showing the data set from the Blanco and Mayo telescopes at the NOIRLab Cerro Tololo and Kitt Peak sites. And you can see here that it doesn't cover quite all of the sky, but quite a large fraction of it. So again, it's been really awesome to have the chance to explore these data sets with our Backyard Worlds participants. And I'll leave it there and take any questions.
Fantastic, Aaron. Thank you so much. I am here from our YouTube audience. Again, welcome to all to Live from NOIRLab here with our host, Rob Sparks, and our science guest today, Aaron Meisner. So Aaron, let me just start off by saying all of your Backyard World colleagues are blowing up the chat. They are totally supporting you. It's amazing hearing everything that they are talking about. One particular comment, though, someone mentioned finding this was an L-type dwarf, and I asked in the chat if that was common or not, and then of course they said no and started talking about T and Y-type dwarfs. I personally don't know T and Y-type dwarfs. Could you enlighten us a little bit?
Yeah, great question. I kind of was avoiding in my main talk going into too many details about this, but yes, it's great to know that some of our very talented and very well-informed volunteers are on here asking the tough questions. I did advertise to the Backyard Worlds group, so I guess it's not surprising that some of them did attend. So there's this, what's called the spectral sequence. And so the coolest objects that are known as stars are called M dwarfs. And these are at the very lowest temperature, something like 3,000 Kelvin versus like 5,700 Kelvin for the sun. So these are much colder than the sun, but they're still hot enough and massive enough to be properly considered stars. When you go slightly cooler than that, you get into what's called the L dwarfs, which start to be in this maybe sort of the 2,000 to 3,000 Kelvin range in terms of their temperature. And these are, for the most part, brown dwarfs in the sense that they're not performing fusion in the same ways that stars are. So they're much fainter. And L dwarfs are also generally kind of rare. So L dwarfs are definitely one of the high priority objects that we're looking for in Backyard Worlds, and we've discovered many of them. But you can go even colder than the L dwarfs, which is what we call the T dwarfs. And so T dwarfs are sort of characterized primarily by the prominence of methane influencing the way that their light shows up in their spectrum. And T-dwarfs are one of the key types of objects that we hope to discover in backyard worlds, because they're really best discovered with a data set like WISE that has a view in the infrared wavelengths at several microns. And then a remarkable discovery that came out of WISE sort of 10 years ago about now is what's called the Y dwarfs. So WISE actually expanded and extended the known spectral sequence of stars to a totally new type called the Y dwarfs, which is even colder than the T dwarfs. So we're talking less than 500 Kelvin. And this is starting to be really into the sort of almost planetary regime here, where we think that at these cold temperatures, you can actually have water clouds happening in the atmospheres of these objects. And so these are really, really interesting scientifically as sort of laboratories for studying the exoplanet atmospheres by proxy. And also they're super hard to detect because they're so faint. And that's why we need to have lots of eyes on this data to scour it and find the super faint Y dwarfs.
Thank you, Aaron. Okay, I will continue with another comment and question from the YouTube audience, and I'm just going through and picking some. I have to say, Aaron, there is a very lively conversation here. I'm really, this is a really fantastic topic that you've gotten everyone really excited about. So we have a question, I had a question early on from Liz Flemings from Memphis, Tennessee, and she wanted to know how could she find out about local citizen science programs or projects that she could join. She happens to be a teacher, elementary school teacher, and wanted to know if there's a way to connect with something that she and her students could participate in.
Yeah, so there are a few resources for this depending on sort of different institutions or agencies that you go to. Let me just highlight a couple of the best ones that I know of. There's certainly many more that I probably don't know of, but one is called SciStarter, and it's just a website, and it is sort of like an inventory of a large number of different citizen science projects across all different disciplines. So not just astronomy, but as you're saying, there's many that are, like are more community driven in the local environment. So like looking at different types of wildlife or pollution, for example, in your neighborhood. And so I would say SciStarter would probably be a good place that would have the full spectrum of, astronomy to other sciences to more community driven projects. Then another one that is more specific to astronomy, but not entirely specific to astronomy, is NASA now has its own citizen science specific website where it has a listing of all different projects, and these span from astronomy, like backyard worlds, to environmental, where it's sort of about monitoring climate, and then other things like ecology, even where they have projects about penguins in Antarctica. So those are the places I would start: the NASA Citizen Science website and SciStarter.
Thank you so much, Aaron. I put the link to SciStarter just in the chat, and when I finish this next comment, I will add in the link to the NASA Citizen Science link. I apologize, y'all. It just started raining, and so I just had to shift my computer, so that's why the video just moved. I apologize. Okay, so one of your colleagues asked, did you speak of your latest submission to archive?
Wow, good question. A little bit of foreshadowing here. So we have a big paper that's still a little bit under wraps that has 100 of our very coldest discoveries from backyard worlds. It's been accepted now, so it's great to see that we have this peer-reviewed paper that has 20 of our citizen scientists listed as co-authors, which is close to a record. I don't think it's quite a record across all citizen science projects, unfortunately. And so I would remain a little bit tight-lipped about this for now, but I would say to keep an eye on NOIRLab's communications websites for the coming couple of weeks, because there'll be a lot of really fun material shared about these amazing backyard worlds discoveries to sort of promote the message and reward all of our participants for the great work they've done on this.
Excellent. Thank you, Aaron. Let's see, our last comment that I'll leave with, and then I'll come back after your next section, is from Jim Walla. Jim says, Hi, Aaron. Jim Waller here. Nice job. And follows up with this question. What do you think are the odds of some of our backyard world objects being early on the James Webb Space Telescope agenda?
Yeah, thank you, Jim. Jim is one of the 20 folks that I was alluding to who's credited as a co-author on this upcoming paper for his really awesome cold brown dwarf discoveries that he's made. With regard to James Webb Space Telescope, absolutely, that's something we have our sights set on, because WISE was in large part meant to be sort of a survey discovery mission that helps us pinpoint the exact specific places on the sky that we want to look at and that will be most scientifically valuable for JWST to spend its time on. And so certainly the Backyard Worlds team is planning to submit at least one, if not many, James Webb proposals to look at these brown dwarfs discovered by our participants. And I suspect that these objects are, sufficiently interesting to the broader community that many other members of the community will take these same objects and put them as part of their other proposed observing programs for JWST. And I do think we have a real shot at this because, like I said, we've used Hubble and Spitzer now to look at Backyard Worlds discoveries. So, JWST, of course, it's super precious observing time, but that would seem to be the natural evolution that we're moving towards.
Thank you, Aaron.
Thank you for facilitating the questions, and thanks to all the Backyard Worlds participants who joined in to ask them.
Do you have a next section of your presentation, or is it okay if I ask another question from our audience?
No, that was my presentation, so.
Okay, fantastic. If it's okay, then I will go ahead with this question. And the question is, I apologize, I don't want to mispronounce our guest's name, so I will just read the question. And the question is there any algorithm based on AI that can detect these slowly moving objects to help us identify potential candidates as a first step before humans look at the data?
Yeah, that's another really good question. And it's a question that comes up often is, we sort of see potentially, you could view it as a dichotomy of citizen science on one hand, which is using people to solve really hard and painstaking research problems versus, on the other hand, potentially using artificial intelligence to automate everything. And so one thing that we've persistently seen with Backyard Worlds is that the feedback we get about the objects of interest, these cold brown dwarfs, in the imaging data from our human participants is much more reliable and useful than what we get by just running a fancy computer algorithm. And this really just simply has to do with things like it's really hard to align the data precisely. So for these slow moving objects, you get a lot of false positives from the computer algorithms. And that's something that people are very good at looking at and detecting, well, maybe the images are just misaligned slightly versus this is a real interesting discovery. And just one last note on the machine learning topic. I think that I would view it as a really great potential for a synergy here, exactly as was suggested by the question asker, that you can use citizen science and machine learning together to really amplify one another. So one example would be to have machine learning make a big selection and then have that further vetted by the volunteers. But it can actually go in the opposite direction as well, because we have all these great labels of, for example, true positive versus false positive coming from the annotations provided by our citizen scientists. And so those can in turn be fed into the machine learning itself to improve its classification. So it can actually go both ways with the connection to machine learning.
Thank you, Aaron. Could you, for those of our people in our audience who may not be as familiar with machine learning as some of your some other people who are joining us today, could you just maybe in one sentence tell us what machine learning is?
Yeah, the way I would explain it is you give computers examples of, say, good and bad objects on the sky. And then from those examples, the computer can learn to make an algorithm that applies to other objects and decides automatically whether those are good or bad. And so, that's a natural thing to want to think about in the context of rare object discovery in large astronomy data sets.
Thank you. So we have a comment here that mentioned the new, in Zooniverse, you have a new project, the Catalina Sky Survey. Could you tell us about that?
Yeah, so that's actually not personally my project. I did see the announcement about it and it looked really cool. It ties back into this idea of potentially detecting something like Planet 9 or other Pluto-like objects further out in the outer solar system. And so the way we're doing that with WISE, it makes a certain presumption that you need to have a planet that's massive enough to be bright in the infrared, which means it needs to be emitting its own self-luminous emission through its own gravitational contraction. But WISE won't be good at detecting these distant solar system objects that are just rocky bodies, like say a rocky version of Earth or Pluto. And so using something like Catalina Sky Survey tackles that part of the problem, where if this is an object that's small and you can only see it in its reflected sunlight in the visible light portion of the spectrum, then you would want to be looking for it in Catalina Sky Survey. So I definitely think that project is a great idea, and I hope I can have more of a chance to try it out in the near future.
Yes, Aaron. Yes, absolutely. Thank you. It's been in the chat. There's quite a few people who were familiar with the Backyard Worlds program outside of your volunteers and colleagues, but just others in general who had participated in Zooniverse and had seen some of the different links that are there, including yours. And I have to say, me personally, I have done quite a few citizen science projects, Zooniverse, SETI at home, Einstein at home, and absolutely loved it. But I have to say that as an adult, I found that, pretty approachable. Are there some projects that you'd say are more geared towards maybe parents or adults working with a young person to help them learn how to approach a science data set? Because a lot of students have never done that.
Yeah, that's a really good question. So we have many of our participants in Backyard Worlds are high school age, and we have seen uses of Backyard Worlds in the classroom down towards, I would say, the sort of early middle school age. But for younger children than that, I do agree it's a little bit technical and intense to really ask of them. I would again point towards SciStarter, because I believe that every time they list a project, they sort of list the appropriate age group for it. And so that would probably be the best point of reference to get concrete ideas about which projects are appropriate for which age group. And I would also just end by saying that Backyard Worlds is very interested in this idea of adapting to create more education and enrichment type materials. And so we're hoping that we can eventually get NSF funding to allow us to do that, because I think that would be really awesome.
Definitely, more resources out there available to everyone can only be a good thing. I'd like to say thank you so much, Aaron, from our YouTube audience. I will pop back in if there are any last comments or questions, but it looks like we have lots of good job. Thanks for the presentation. Yes, a lot of that, which is really amazing, Aaron. I mean, you've really got a good conversation going here. And then we have a question from, it looks like Von Billy, and I apologize if that is incorrect, but the question is, and no pressure, but where do you think Planet 9 is hiding?
Yeah, that's a tough question, because I've done, in addition to Backyard Worlds, I've done my own sort of automated full sky searches for Planet 9 and come up empty-handed. And so one aspect that I think is really promising on the Planet 9 search is coming back to another NOIRLab upcoming program is the Rubin Observatory in Chile. and has this legacy survey of space and time, LSST, that it'll be doing over 10 years, starting a couple of years from now. And that will survey, maybe 2/3 of the entire sky every 3 nights, and with a really great depth in visible wavelengths. This is a 6+ meter telescope we're talking about here. And so that will be really, really great for detecting Planet 9 if it happens to be this scenario I mentioned before, where it's super faint and we're only seeing it in its reflected light from the sun. So I have to say that Rubin and LSST are some of the things that most excite me about the future of Planet 9 searching, in addition to continuing with the archival data we have from WISE and, say, Catalina, for example.
Thank you so much, Aaron. That was a fantastic response. And thank you again for mentioning one of our other NOIRLab facilities, the Vera C. Rubin Observatory. I did just put a link to that in our chat so that anyone in our audience can follow up on finding out more details about Vera Rubin's capabilities. Thank you so much. And I will end with this last comment from Larry. He says, "Thanks, Aaron. You knocked it out of the park."
Yeah, thank you, Larry. I'll probably talk to you tomorrow on the Backyard World Science Team call, but thanks a lot to all the folks from Backyard World for your support.
Yes. Thank you, Aaron. It's been great having you here. It's been a very interesting hour, and I think we have some more announcements to come from Backyard World soon. So I've just advised people to stay tuned, right?
Yeah, exactly. Thanks a lot to NOIRLab, who's really going to help us in the coming weeks get the word out about some of these great discoveries and opportunities to get involved. So thanks also to you and Jamika for all your work hosting this.
Yes. You want to come back on and say goodbye, Jamika?
I would. It is always a pleasure to be here joining the Live from NOIRLab. I always learn so much, and it's always a lot of fun. So thank you again, Rob, for having me as your moderator. And again, Aaron, this was amazing. Thank you so much. And I have to say, you will see a little message from Jamika Marshall on your Backyard World's website asking to join, because I had never, I didn't know about this project, and I'm really, really curious. So you've definitely really engaged me. Thank you, Aaron.
Yes.
Okay. Yeah, thanks again.
And of course, we invite everyone to join us again next week, Wednesday at 1 p.m. Mountain Time. That'd be 4 p.m. Eastern Time, 10 a.m. Hawaii time for our next Live from NOIRLab edition. So thank you very much, and we hope you'll join us again next week.
Thanks. Bye.